Hello everyone and welcome to this talk. My name is Alec Pickel and I'm from Technical University of Munich from the Chair for Computational Photonics. Today I'm going to be talking to you about completely positive trace-preserving methods for the Lindblad equation. My co-authors are Michael Riesch and Professor Jirauschek, and this talk is in the scope of the 20th International Conference on Numerical Simulation of Optoelectronic Devices. Let's begin with the Lindblad equation. The Lindblad equation describes the dynamics of open systems in quantum mechanics, which are represented by the density matrix ρ. In the equation number 1, you can see the Lindblad equation, and here H is the Hamiltonian of the system and D are the dissipation terms. We can use the Lindblad equation to simulate, for instance, a lot of things in quantum optics, like quantum dot and quantum cascade lasers, condensed matter physics, atomic physics, and so on. In our research, we use the Lindblad equation in the scope of Maxwell-Bloch simulations of quantum cascade lasers. In the figure, you can see in colors different energy levels, and in gray you can see the conduction band profile of a material. The way that quantum cascade lasers work is that when electrons change their energy states, they also emit photons, and those photons are basically what causes the lasing. In our research, we're trying to simulate this process, and by doing that, push forward the state-of-the-art in QCLs. Solving the Lindblad equation. This is the whole simulations. They all come down to repeatedly solving the Lindblad equation time step after time step. We know that analytic solutions in most cases do not exist, so we have to solve it numerically every time step. We want to do this as efficiently as possible. But how do we solve such an equation numerically? Numerically or mathematically, this is simply a system of coupled ordinary differential equations. We can try to solve it by using a standard time stepping scheme where we have the density matrix at time m or n, then we apply some standard time stepping scheme u, and then we get the density matrix at time n plus 1. We can use, for instance, Crank-Nicolson or Runge-Kutta for that. But it turns out it's not as simple as that, and that's why we're having this talk today. Turns out, because we're simulating physical systems, we have to also uphold all the physical properties of our simulated matrices. And in our case, the density matrix ρ is Hermitian, it's positive semi-definite, and its trace equals to 1. So in every time step or every update step must preserve those properties of the density matrix. Otherwise we're violating laws of nature. We know that quantum operations are represented by completely positive trace-preserving, or CPTP in short, maps. When we want to prove that a time step is completely positive and trace-preserving, we're using the Krauss theorem, which says that if the map or update step is CPTP, then we can rewrite this update step as the sum over I, mi ρ, mi Hermitian, and those mi's are Krauss operators, and they have to fulfill this condition that the sum over I, mi Hermitian equals the identity matrix. Now the question arises, which numerical methods provide such an update step? So Biedegaray and her co-workers in 2001 demonstrated that Crank-Nicolson does not preserve the properties for the systems which are bigger than n bigger than 2. So n here is equals number of levels, and they proposed operator splitting. We know that matrix exponential methods that solve the Lindblad equation exactly are by definition CPTP. And what about approximations? We know that predictor corrector methods and Runge-Kutta are not CPTP. So now we have to talk about representations of the density matrix, because different representations lead to different methods. First, we have the regular representation, where we have the density matrix as an n by n matrix, complex matrix, and L is the superoperator which we saw in the first equation. We have the Liouville space, where we can basically stack the columns of our density matrix to get the n² complex vector R. And then we can rewrite our superoperator in a n² times n² complex matrix L. We also have the Bloch vector, pseudospin, or coherence vector representation, depending on which paper you're looking at, where we are using the redundant information, which is the Hermitian property, the trace equals 1 property, and the positive semi-definiteness of the matrix, to actually get rid of one element or one population in the vector. Plus, we now have a real vector instead of a complex vector, as was the case with the Liouville space. We can construct such a representation by using the generalized polymatrices, but I'm not going to go into depth into how to construct such a representation right now. And then lastly, we can have an alternative real-valued representation which exploits the Hermitian property. And here we basically have, similar to the Liouville space, we have L as a matrix and not as a superoperator, which is a n² times n² real matrix. And then we have the R, our density vector, which is n² real vector. So here we have real entries, but we have bigger matrices than in the regular representation. So how can we now, given all of those representations, solve our Lindblad equation for one time step? Bitegaray and her co-workers in 2001 proposed operator splitting in the regular representation. We named this in our measurements os-reg-cayley. The idea behind this is to use the operator splitting to split the operator into a time-dependent and a time-independent part. We can calculate the time-independent part at the beginning and then just apply it every time step, and we calculate in every time step the time-dependent part. Then we can use all of those to construct a solution. And as you see, they proposed that we can use the Cayley transform as the approximation for the matrix exponential to save some cost. Then we have, again, operator splitting, same as above, but this time in the coherence vector representation, which was proposed by Risch and Jirauschek in 2017. We call this operator splitting os-CVR RODR, where for the matrix exponential, we're actually using the Rodriguez formula to calculate matrix exponential. And then the third one would be to use the real value representation, or RVR. And in this representation, we basically have to only calculate directly the matrix exponential and then multiply it with the density vector. We implemented the method from Almoui and Higam from 2011, which basically allows us to directly calculate this action of the vector on matrix exponential instead of explicitly formulating the matrix exponential and then applying the vector. So we wanted to see if we can get some speed ups by using this method. Now, our performance measurements were done on an Intel Xeon CPU. We measured single thread only. Our compiler and compiler flags you can see here. Also, we used the eigen library for matrix operations. And we measured performance in absolute grid point updates per second. So the performance is basically grid points, spatial grid points times grid points divided by the execution time. And our test case was a setup from Marskar and Österberg from 2011. And we scaled this setup from 2 to 10 levels. Some implementation notes. For the os-reg-cayley, so operator splitting, regular representation, and the Cayley approximation, we used Eigen's inverse function instead of the Faddeev formula because they were not readily available for systems with levels 5 and up. Here are our results. In the graph, you can see the results, and on the x-axis, you see the number of energy levels n going from 2 to 10. On the y-axis, you can see our measured performance in grid point updates per second. This is on a logarithmic scale. And then you can see the 3 different methods in 3 different colors. So the blue one is operator splitting, regular representation with Cayley approximation. In green one, you see the action method and the real value representation. And in the orange one, you can see the operator splitting CVR, coherence vector representation, with the Rodriguez method for the matrix exponential. Let's discuss the results a bit. So first, theoretical comparison of different methods. We know that the os-reg-cayley uses operator splitting and Cayley approximation, which makes it susceptible to numerical error. Those are basic because there are 2 approximations happening. Then we have the operator splitting, and in the CVR plus Rodriguez, which has a smaller numerical error because we're only using numerical splitting, but we're calculating the exponential directly. And the third one, the action one, solves the Lindblad equation exactly, and the error is up to numerical precision, so we can basically go from highest error to lowest error, up to down, up to bottom. And now the scaling with respect to energy levels. I think it's best if we move back to the results. In blue, you can see that the reg-cayley has the best times for levels 4 and up. Though this was kind of expected because it's using the matrices that we're calculating matrix exponentials from are n times n matrices. So this was kind of expected. Then we have the Rodriguez in the orange color, which is very good for levels 2 and 3. Again, because we're basically using these, we're throwing out the redundant information, thus we have less, the matrices are smaller, but it scales really poorly for higher level systems. And then we have the action method in the real valued representation, which was kind of surprising, but it scales really well for bigger systems. And this is why this is surprising, is because the real valued representation basically has matrices of size n squared times n squared, and it scales the same as the reg-cayley, which has matrices of size n times n. Exactly, it doesn't beat Cayley, but it scales really well, or it scales on par with reg-cayley. Plus it has this benefit of being a direct method. Okay, so to conclude, we evaluated 3 CPTP numerical methods for numerically solving the Lindblad equation. We saw that os-reg-cayley shows the best performance so far, but also that the action in the real valued representation gives reasonable performance with less numerical error because it's a direct method. And what do we want to do from now on? We want to look into the polynomial methods, such as Newton polynomials or Faber polynomials. We want to further profile and optimize the implementations, because we're implemented all of the methods in C++. We want to further optimize them and see if we can get even more speed ups by using, for instance, sparse matrices, dynamic matrices, or fixed size matrices. We want to check the parameter determination routine in the action method, if we can gain some speed up there. And because this time is very, we like GPUs in this time, we want to try to work on a CUDA implementation and see if we can parallelize the solvers on a GPU. So this would be all from my side. Thank you all for your attention, and we would also like to thank the German Research Foundation for funding and the Gauss Center for Supercomputing for funding this by providing computational time. Thank you very much. And these are the references.